the deformation. It's a truly two-way coupled problem. The fluid model is your independent model because it won't be affected by the structure. The monolithic approach have one set of equations, one single solver, and that single solver is solving both physics at the same time, essentially. Compressibility and density plays a key role to distinguish between strong and weak coupling. It's very rare that we have one person who has a detailed knowledge about both physics.
The word CoSimulation, what does it actually mean and what's the alternative?
The dependent model, we really have two dependent models, and hence we need to solve them concurrently. CoSimulation, my experience, comes with a lot of challenges. It's a productivity killer. One-way coupled solution procedures are a lot easier because then you don't need to exchange data back and forth. If you want to be successful, I think you really want to start as simple as possible.
This podcast is sponsored by Siemens Digital Industries Software. Learn more about their simulation and test solutions by clicking the links in the description. Build a better tomorrow faster with Simcenter. Alright, the first ever podcast on this channel on fluid structure interaction, ladies and gentlemen. And I'm very, very delighted to welcome Rafael to the show. Welcome.
Thank you. Thanks for having me.
Before we delve into FSI and the intricacies of this method, can you give us a little bit of a background, like who are you in the first place and what are you working on at Siemens?
Yeah, sure. So my name is Rafael, and I'm with Siemens, or with the company, I guess I should say, for a little over 13 years by now. So I started in the days when the company was still called CD-adapco, and there I started in the Department of Engineering Services. And I used to work in the services department for about 2 years, doing paid CFD projects, working at customers on site every now and then. From there, I transitioned into the role of a global specialist for FSI, fluid structure interaction, essentially. And then I was looking after that topic for several years. And from that role, I transitioned into the role of a product manager. I'm still looking after fluid structure interaction, and that's what I'm still doing today. Yeah.
Sounds great. Could you maybe give the audience a little bit of a glimpse? Like, how was it for you? Like, how did you get into fluid structure interaction to begin with? I mean, you could have chosen any topic. Why FSI to begin with?
Yeah, that's a good question. So I studied mechanical engineering in Germany, and at some point I was doing an internship at a company, and they were building heat exchangers for automotives. And they had a big simulation department, so a group of structural analysts doing finite element analysis, another department doing more thermodynamics, you could say, and a third department doing CFD. And that company, while I was doing my internship, was going through, I guess you could call it a rough patch. Essentially, people were about to be laid off. And it was striking to see that there was one guy, it was obvious that he would be the last to lose his job. And it was the guy who was sort of the connection between the fluids department and the structural department. If you wish, he was the only one who understood both worlds. He was an FSI expert at the end of the day. And I felt like, okay, maybe that could be a useful combination of knowledge to have, being able to understand structure mechanics and being able to understand fluid mechanics, because there are quite a few for each discipline, but there are very few with a combined background. And that then motivated me to do a second degree, actually in Stockholm at KTH, where I then studied in a master's program focused on fluid mechanics. I had my degree from Germany on structure mechanics, but then I said, okay, let's become that guy, right?
Yeah, very cool. I mean, the name is already giving it away, Rafael, right? I mean, we say fluid structure interaction, so I think it's quite obvious what we talk about, but maybe can you give us a little definition of what FSI actually means?
Yeah, sure. So obviously we have fluid and structure, that's clear, and then we have the interaction between both. And if we want to look at it in a more mathematical sense, you could say it's a surface coupled problem. So you have the fluid pressure acting on the structure, deflecting that structure eventually, and then you have the deformation of the structure that impacts the flow around the structure. So there's a coupling in both directions. And essentially, if the coupling is equally strong in both directions, you sort of have a symmetric problem, if you wish, and that's a two-way coupled problem. But the strength of the coupling can also be asymmetric, meaning it can be very strong in one way, but very weak in the other way. And then you have sort of a one-way coupled problem.
Yeah. How do you actually represent a structure in an FSI problem? I mean, we're talking about a mesh, right? Are there any other configurations that you see?
Yeah. So I think if you sort of want to classify FSI or figure out what kind of problem you're actually dealing with, there's typically three questions that are good to ask in my experience. The first question is is the coupling strong or weak in the direction fluid to structure, for example? And is the coupling strong or weak in the direction structure to fluid? So once you have answered those questions, if it's strong, then obviously it's two-way coupled, or it's one of those asymmetric configurations where you have a one-way coupling structure to fluid or one-way fluid to structure. And then the third question essentially is really, what's your structure? Is this something that needs a continuum representation, meaning is it a body that will deform, deflect, or is this something that eventually you can model as a rigid body, like a 6-degree of freedom body, which is typically done for marine applications when you model like how a ship moves through a series of waves or something like that. If you don't care about stresses anywhere in the hull, you rather want to know the pitch motion, pitch frequency, what have you. It's like such a 6-degree of freedom body representation is very useful. And with those three questions, you can then sort of, whenever you look at a problem, sort of classify it and understand what kind of applicational problem you're actually looking at.
Mm-hmm. Do you have any other examples apart from the marine example that you just
gave? Sure. Yeah. So one example that I like to use to demonstrate like a one-way coupling in the direction fluid to structure is, for example, the rear wing of a sports vehicle, a fast vehicle, where you have a rear wing. So if you want to design that rear wing and, for example, the mounting posts, and you want to dimension them, you obviously need to know like what is the load on those, and that will obviously come from the fluid flow. So you clearly need the information about the pressure distribution on your wing to predict those forces. But then on the other hand, probably that wing will deflect only very slightly, and that will probably only have a very minor effect on the aerodynamics or the vortex shedding or what have you. So this is typically a problem which is very strong coupled in direction fluid to structure, but weakly coupled in the direction structure to fluid. Of course, it always depends what the engineering question is that you're trying to answer. But in this example, I was saying, I want to predict the stresses in the mounting posts, and there it's probably a good approximation to say it's one-way coupled. A good example, the other way around, so more in the direction structure to fluid is, for example, is a peristaltic pump. So that's essentially a tube pump, and you have inside the pump a rotor, which is pressing the tube. And if you want a rough estimation of like what mass flow rates you can expect that pump to produce for a given speed of your rotor, then you can probably say, okay, the deformation of that tube is purely a result of the structure mechanics, and it's really prescribed by the roller pressing that tube together. And then you can just prescribe that tube deformation in your flow model, essentially. And that would be probably a good first approach to predict roughly the performance of the pump.
That's interesting. So you talked about the one-way coupling, so that also suggests that there's a two-way coupling. Could you explain like what the differences are and what this actually means?
Yeah,
mathematically.
absolutely. So a good example for that would be, for example, your heart valve, right? That opens and closes, and it's a periodic problem, obviously, and depends on your heartbeat and how your heart is pumping the pressure or the fluid through your body. And here um, you cannot really say that it's only coupled in one direction, right? The deformation will affect the flow, and the flow will affect the deformation. In a sense, it's a truly two-way coupled problem. Whereas in the one-way coupled problems, you can always say that there's something like an independent model. In the example of that wing, you could say the fluid model is your independent model because it won't be affected by the structure deformation. In the tube pump example, you could say the independent model is really the structural model because we say like the deformation of the structure is not dependent on the flow, and hence you can always say there's an independent model that you can solve first and a dependent model that you can solve next. And in a two-way coupled problem, both models are essentially dependent. They depend on one and another. So that's really the fundamental difference. It's really a symmetric problem.
Mm-hmm. When we talk about, I think one question I had also probably that interests the audience is the compressibility effect. Like, is that critical when you model like an FSI problem? And how do you take that into consideration when you set up such a problem?
Yeah. So what comes to compressibility or what comes to two-way coupled problem, especially, it's interesting to realize that there are some problems which are strong coupled and others which may be are rather weakly coupled. And one key factor that affects this degree of the physical coupling is really the compressibility or the density. So liquids like oil, not water, obviously they have a high density and they are nearly incompressible. And those are typically, whenever you have a liquid in the mix, you're most likely looking at a strong coupled problem. Whereas when you have something like a gas, air, for example, that is very light and compressible, most often you're then looking at a rather weakly coupled problem. So the compressibility and density plays a key role to distinguish between strong and weak coupling. To put it differently, the density ratio, so the ratio between the density of your structure and the density of your fluid is crucial. The closer that gets to one, the stronger your physics are probably coupled together.
Yeah, but I would imagine I'm not an FSI expert by any means, but I had like maybe one lecture in uni back in the days. Like when you set up such an FSI problem, is there like a kind of a checklist or a questionnaire where you have to basically check about the compressibility effects and some other things before you can even start or set up the simulation to begin with? Because I can imagine like if you use a Siemens product, for example, I think there's so many settings that you can tweak, so many parameters. So are there some kind of key points that you need to check in order to get started before you even get started?
Yeah. The number one thing you always want to check before you get started is that each model runs on its own, right? So you don't want to start by doing an FSI simulation if you're not even confident that the individual physics solve correctly, essentially. So you always want to make sure first that, okay, my flow solution without deformation solves fine, and also my structure model solves fine without a flow. So once you've done that, then really you either you already know whether your problem is one way or two way coupled, right? Then you can choose the most appropriate way to solve your problem. And if you're uncertain, then you can always say, okay, I try to do it two-way coupled. In that sense, I'm not making a modeling error, and maybe later I can figure out myself if the two-way coupled approach is really required or not. And then you need to make sure, or you want to look at like Is my structure very compliant, or is it rather stiff? Do I have a lot of mass in my structure, a lot of inertia, or is it light and compliant? And then the flow side, you want to look at things like what's my compressibility, what's my density, is it a liquid, is it a gas?
Mm-hmm. When it comes to the modeling approach, Rafael, there are two different ways to actually model an FSI problem, namely the monolithic approach and the partition approach. Could you maybe separate those and define what this actually means, and when would you choose one over the other?
Yeah. So the monolithic approach really is an approach where have one set of equations, one single solver, and that single solver is solving both physics at the same time, essentially. So it's one solver, one set of equations. And typically that is a solution which is very problem specific, and usually I need to if I want to code something like that, I need to code each and every boundary condition for this monolithic framework, essentially. And it's, in my experience in the industry, there are very few instances where it's actually being used. It's more an academic thing in a sense. What is way more common is the so-called partition approach, where really have two solvers solving two sets of equations, and then I have an interface in between, and over this interface I exchange pressures and displacements, and for example, and then I try to iterate out what's the configuration in which the equations are satisfied for both of my physics, so the fluid and the structure, essentially. So that's the partitioned approach, and that's way more common. Often it's being realized through CoSimulations.
Mm-hmm. When you have a basically the solid interface and the fluid interface, so what are some kind of modeling, I would say, considerations that you need to take into account? Like we have space resolution, time resolution. Like yes. What do you need to make sure that actually something doesn't diverge in the simulation?
So from a modeling perspective, really, I mean, obviously it would be great if we could completely decouple the two, in the sense that I can choose whatever space and time discretization is most suitable for my fluid and for my structure. Then I can look at, for example, my time and length scales that I'm expecting my flow, my structure model, and I choose the mesh size and the time step size, which is suitable considering what I'm expecting there. That has one other great advantage, obviously, if we think of it from a more practical point of view. It's very rare that we have one person who has a detailed knowledge about both physics. So it's way more common to encounter a scenario where actually a fluid mechanics expert wants to cooperate or work together with a structure mechanics expert. And if we have a setup or a workflow or an approach that allows us to choose independent discretizations for the models, then it's a lot easier for those experts to successfully or to cooperate in a productive manner, because they don't need to know anything about the choices of the other models. So they just look at the physics they need to solve, and they choose whatever is the right choice for that. That then leads to requirements on the spatial discretization side, that you need to interpolate over a surface. We said initially it's a surface coupled problem, meaning we need to interpolate from one surface mesh to the other surface mesh, pressure versus displacement. So it's a spatial interpolation. And then if we choose independent time step sizes, we also need to interpolate in time, obviously.
Yeah. I'm wondering, let's say the fluid mechanics expert, like they look at maybe some dimensionless numbers, like the Reynolds numbers, for example, and the structural engineer is considered or like cares more about other numbers or metrics. How does the information interchange happen at the interface? Is it like only a problem of the solver, or does the engineer have to think about the information interchange?
Ideally, the user doesn't really have to worry about that, right? But that then really comes down to the question, what kind of tool or how are you actually trying to solve your fluid structure coupled problem? Is this a solution like that is a CoSimulation that is eventually you've developed yourself, where you might be responsible, or where you as a user may carry quite some responsibility to ensure that this data exchange is happening at the right frequency and the right point in time, so that the time points actually match, or whether that's more a product that has been really geared towards FSI, and where you as a user don't really have to worry about it, and the algorithms are taking care of that for you.
Okay, that makes sense. Yeah, you mentioned, Rafael, the word CoSimulation. What does it actually mean, and what's the alternative next to CoSimulation?
So CoSimulation is typically the approach which is being used to model two-way coupled problems, because as we said earlier, right, in the two-way coupled applications, we don't have an independent and a dependent model. We really have two dependent models, and hence we need to solve them concurrently at the same time. We cannot solve them in sequence, meaning one first and then the other. We need to continuously solve them. And that, of course, means that we are exchanging data between one model and the other with a high frequency. So we don't want to write data to files. We rather want to keep the data in the memory. And then a CoSimulation comes in really handy. The other approach is more what I would refer to as a single simulation approach. That's what we're using at Siemens with Simcenter STAR-CCM+, where you really try to model both physics within one single model, meaning you have one single executable, you have both models set up in one simulation, and then you solve that in one go. The algorithm behind the scenes is still a partitioned approach, but you're not launching two independent executables which then do a handshake and start the CoSimulation process. So that's what I would call it, a single simulation approach to multiphysics.
Yeah. What are some of the other disadvantages when we talk about a CoSimulation, or why it's not often a good solution in the first place?
Yeah, that's a very good question, right? So if we want to start maybe with the positive aspects of a CoSimulation, right? Or if I wanted to sell you a CoSimulation, what I would tell you are things like that, yeah, this enables domain experts to work with their native CAE tool, right? So whatever the structure mechanics person has been using over years and the fluids person has been using over years, they can stay in their environment and just do the CoSimulation. And you can couple your models only on a need-to basis, so just when you really want to. But that is, yeah, it's true, but it's not the whole story, actually. The very negative view on a CoSimulation could be that you say, like, okay, the CAE vendor is really outsourcing all the synchronization problems to the user. In a sense, now I'm responsible to make sure that both applications start successfully, that they perform the handshake, that both get the license that all the data is synchronized, that I'm using the same units in both models, that the models are correctly aligned in space in both models, and so on and so forth. So CoSimulation, in my experience, comes with a lot of challenges. It's very difficult for the user to run those CoSimulations, and it really reduces your productivity, because even if you want to post-process your results, right? Typically, if they are an independent product, you cannot see your solutions together. You first need to export them somewhere and import them again to look at the coupled results, really. Or if you want to look at the solver output, right? You have one solver output, another solver output, and then you need to figure out what matches actually what. So it's extremely difficult to run such CoSimulations, and I've helped customers over the past 13 years to run CoSimulations. We also offer some, And the number one struggle is just to get it up and running on an HPC environment where you don't know upfront how the different jobs will be distributed, right? On which node will be the fluid model running, which node will be the structure model running. All that is typically unknown upfront because you're using a queuing system that will ultimately decide how that is being distributed. So it's a productivity killer.
Yeah. I'm wondering, when we talk about the strong two-way coupled applications, is there some challenges when we talk about that application in particular?
Yeah, strong coupled problems are typically very challenging to solve, especially for partition solution procedures where you have two solvers working on two sets of equations. One example that I always like to use to illustrate is by imagine you have a balloon, right, and it's filled with water. And then you take your finger and you poke into it. Right? So what is happening now when we try to solve this with a partition approach? Let's say we start with the structural model, right? So we have the finger, and that will poke into the balloon, into this flexible membrane. So that membrane will deform, right? And when we compute that deformation, obviously, at the beginning of the simulation, we don't know that there's a fluid inside. So the result will be as if there is no fluid. So that's going to be the first thing that we send over to the flow model, some deformation field. So in the flow model then, we'll update our fluid domain considering the deformation that we just received from the structural model. And then it gets interesting, right? The balloon is filled with liquid, and we even model it as incompressible with a constant density model. Then what's going to happen? Strictly speaking, the fluid model is almost guaranteed to diverge because that deformation field will not be volume conservative. And since we're using a constant density model, that means we are violating conservation of mass. So we cannot find a solution to the problem. If we do the same example, but imagine this time that it would be very compressible, filled with air, right? And we get some deformation field over to our flow model. We update that. We get back some sort of pressure response, right? We feed that back to the structure model, and then we can iterate back and forth. And through this compressibility of the fluid, eventually we'll come to the converged solution where both governing equations for our system are fulfilled at the same time, essentially. And I think, in my mind, that's a good example to sort of demonstrate this compressibility plays a huge role in terms of how easy or difficult it will be to solve a strong coupled problem. And then, of course, if you have a liquid and a lot of mass and of inertia, if we think about Newton's law, sum of all forces equals mass times acceleration. If we predict some deformation and with it some acceleration, right? Because we need to accelerate now a lot of mass, a lot of heavy things, a lot of inertia, right? We need a lot of pressure, or with other words, the fluid will respond with a massive pressure increase if we try to accelerate it because of all that mass that needs to be accelerated. So also the response back to the fluid in terms of a change in acceleration will be a lot of pressure change. And then if you get those huge changes all the time, obviously it's difficult to keep the solution stable or to get it converged to the state where both sets of equations are fulfilled at the same point at the end of the time step.
Yeah. We covered a lot of complex topics in this podcast, Rafael. I was wondering, like an engineer, when they start to set up a simulation, they think about a specific problem. One question they might ask themselves is like, should I only do the structural simulation? Should I only do the fluid simulation? Or should I do both using FSI? Like, what do you think is kind of a check mark where you would say, okay, now it's time to actually use FSI? What for you is the prerequisite?
Yeah, I think that's really difficult to answer in a sense. I think you always need to start with the engineering question that you're trying to solve, right? As what problem am I trying to solve? Why why am I even simulating in a sense, right? And then you really need to put some thought into it and try to understand, like, okay, is it, will the coupling in the direction fluid to structure, will that really have a strong impact, or will the coupling in the direction structure to fluid have a strong impact? Yeah, and then my advice would always be, whenever you can, don't do a two-way coupled simulation. Don't make your life more difficult than it needs to be. Right? Those one-way coupled solution procedures are a lot easier, because then you don't need to exchange data back and forth, and the physics aren't coupled, so you can solve your independent model, and after that you can use the results of that independent model to compute the dependent model. It's a lot easier. So unless you really need to, I wouldn't do it. And if you're really uncertain, my advice would be, maybe you need to do it once, right? If you have a certain application that you're trying to solve over and over again, maybe you need to go through the exercise once to get confidence. Do I need to do it, or can I ignore it? And once you've answered that for yourself, then in the future you will know, okay, we don't have to account for two-way couple, or maybe we do.
Yeah. Before I wrap up the podcast, Rafael, one question I have is, how can someone, especially people listening to this podcast, be successful in setting up their first FSI application? Like some practical examples.
Yeah. So if you want to be successful with FSI, I think you really want to start as simple as possible. So try to start simple, remove any complexity that you can, and then first make sure the individual model solves successfully. So make sure your flow model solves, then make sure your structural model solves, and then attempt the first coupled simulation. And only when you have this like sort of baseline working, only then add complexity. For example, start maybe with a quarter model if you can, right? Maybe you know already from the flow perspective, I cannot use symmetry conditions, so we'll have to model the full thing later. But maybe there is some symmetry conditions you can exploit, and then reduce your model. Start with the quarter model that will solve faster, right? And only when you have that solving, right, then you're way more efficient in getting that up and running. Then extend the complexity, make it a full model, and so on and so forth. So make it simple, and then only step by step. Whenever I've seen customers trying to do the full thing in one go, I've never seen that working. So really start simple and build up to complexity. That's the best advice I think I can give.
Yeah. I don't want to ask the question like, what was the simplest FSI model you've ever solved or worked on? Because I think it doesn't make sense. More like, what is the most difficult one? If you can talk about it, obviously, from an engineering point of view.
I think one of the most difficult ones I've been working on, and I'm still working on it, I think, is it's also the most fascinating one in my mind. It's related to food and beverage packaging, essentially. Mm-hmm. So when you go in your supermarket, you have all those juice packs of all kinds of forms and shapes. Not the bottles, but really those folded cardboard kind of packages or those things like. And if you think about the machines that produce such packages, they're huge machines, and typically you have a feed of a flat material, and then that material gets either rolled into something, and then things are being squeezed. And that's an application where you have a liquid, right? So something incompressible, high density. You have a super compliant structure because that packaging material that has no mass, that has no inertia, that's very flimsy dimension. So it makes the physics very strongly coupled. And then in the specific application that I was looking at, there's also an event that when those individual packages are formed, you have something that I would describe as like a local buckling event, right? So things are being folded, and every now and then it happens that like the structure is under a lot of compression tension, and then something somewhere in the structure does a little pop, and it flips over into a slightly different configuration. And that's, of course, a high-speed event. And as we said before, right, if we want to accelerate the heavy fluid, and if we have a huge change in acceleration from one time step to another, that means we get a huge pressure response, like instantly. You don't see it coming. It just suddenly happens that the structure sort of locally buckles somewhere. And to keep that stable and to make that solve, it's proven to be a true challenge. And I'm still working on that one. And it's something that when you go into the supermarket, you don't see it. When you just grab your back there, when you know what's behind all that, it's pretty interesting.
Yeah, next time I'm going to get some groceries, I'll definitely think about that one for sure. How do you keep yourself up to date, Rafael, with the latest trends in research in FSI?
Yeah, of course. We're primarily papers, essentially, see what's going on in the different institutes which are dealing with FSI. Then, of course, we have very close contacts to several of our customers who are doing very advanced FSI simulation. Yeah, that's I think primarily it.
Mm-hmm. And I was wondering, did we miss anything super important, like regarding fluid structure interaction, Rafael? Anything that we might have missed? Some practical tips. I think we covered quite a lot.
Yeah, no, I think we covered the most important things. We went through this concept of start simple, we discussed one-way, two-way coupling. I think what we didn't really touch on in the realm of two-way coupling, I think, is the difference between dynamic and static. That's maybe something we can briefly discuss. So when we
definitely, go for it.
Static problem, right? So essentially something where you search for a static equilibrium configuration, and a good example would be an airplane wing at cruise condition, right? That wing is going to be deformed somehow, but at cruise condition, that wing is probably not going to vibrate. We're not looking at flutter or limit cycle oscillation or something. So here we really care about what is the deformed configuration, what's the balance between forces. It's a static equilibrium configuration. Then the other example, like I mentioned, the hardware before, obviously there's a lot of dynamic. It's all the time moving, opening, and closing. So very, very dynamic problem. And for those dynamic problems, you need a time accurate solution for your physics, right? Whereas for this wing, probably you don't really care how you get into this static equilibrium configuration. You only want to know how does it look like, right? And then, of course, you can also start to play certain tricks to make it easier to solve. It's a two-way coupled problem, but because you don't care about any vibrations in that configuration, you probably know it's going to be stable, for example. You could increase the density of your solid as a trick, right? So you make it heavier, you add more inertia because, I don't care how that wing reaches this configuration. I only care how it looks like. And once it is in that configuration, the increased density will not have an effect anymore, right? So it's,
Yeah, that's interesting. Maybe one last question I might have, probably an obvious one. How much research is going on in the AI field, like AI for FSI?
There are also things going on, but what I find even equally interesting is how FSI is also starting to be used today in an AI context. So, for example, if you think, I did mention those peristaltic pumps, right, which are tube pumps, and you have a rotor rotating at a certain speed, and then that tube gets pressed down and creates little fluid pockets, essentially, which then translate, and that's how the liquid is being moved. And those pumps today, right, they need to be quite carefully calibrate it, right, to make sure that you get the right amount of liquid out of that pump, considering the subsequent application that you have there. We're seeing trends where people use FSI simulation to train a neural network that will then essentially control the rotor speed such that you get the exact amount of liquid out of that pump without having to calibrate that pump yourself, essentially. So for different kind of fluids, different operating conditions, different target volumes that you want to get out of the pump. So essentially run hundreds of FSI simulations and train an AI model or an AI to control that machine, essentially.
Yeah, really cool. All right. With that, I think, Rafael, we can wrap it up. Thank you so much for being on the show, by the way, and every relevant resource that might be interesting for people, we will put in the description. And with that, yeah, thank you so much.
Thank you. That was great. Thanks a lot.